Okay, so I'm a faculty member here in the Department of Statistics at UCLA. And so today I'm going to give a tutorial, but it's not about a specific bioinformatics method, although my group developed multiple methods. But for this tutorial, I just decided to talk about two general methodology we developed. So hopefully they will be applicable and useful for your research. So that's the purpose of the tutorial. So the first thing is a Neyman-Pearson classification, which is a line of work I have been working on with my collaborators at University of Southern California, which is just across the city, and at Columbia, and also with my student for over the past 3 to 4 years. So I introduced this, which was motivated by biomedical application. And then if I have time, I'll talk about the Generalized R-square, which I have been working on for the past 5 to 6 years, starting as a graduate student, but then finally we came to some solution. But I'll start from the Neyman-Pearson classification first and see how much time we have left. So the binary classification is a very well-studied problem in machine learning, and I will talk about the notations first before I jump into the paradigm. So we have features which are denoted as p-dimensional vectors. So in the biomedical application, they can be health characteristics of a person. And we have a binary class label which can represent a disease status, yes or no. So this is a binary label. So if we want to make a prediction based on a person's health characteristics about his or her disease status, it is a binary classification problem. So we need some training data to train a classifier. So therefore, the classifier is actually a data-dependent binary function that maps from the feature space to the binary space. And the training data is essential. And here we just denote the size as n. So in my talk, I will make a distinction between a classifier and a classification method. So as I said, a classifier is a binary function, but a classification method is a way to construct a classifier from training data. For example, we have logistic regression, support vector machines, or random forests as examples. So therefore, we can see that after the training, the resulting classifier we call H is a function of the training data. And as statisticians, we care a lot about where the randomness comes from. So if we regard the training data as random, then the resulting classifier is also random. And this is important. So we are motivated to study asymmetric error control because of this relationship. So in classification, we have this important quantity called classification error or risk, short as RH. So it is the probability that our predicted label is different from the actual label. So we can just decompose this probability into the summation, and in each term, it is the product of the marginal probability of that class times a conditional probability. So here we can see that this one is the conditional probability that the label is 0, but you predict as 1. And this R1 is the other way around. The actual label is 1, but you predict as 0. So we call this type 1 and type 2 error. So you see that the risk is a weighted sum of the type 1 and type 2 errors. And the two weights are determined by the two class probabilities. So for example, in biomedical application, for example, cancer diagnosis, if we really want to predict whether a person has cancer or not based on his characteristics, then we will have two types of errors. One is that the person is not cancer, but we predict to have cancer. So this error, the result of this error is that patient will be anxious and there will be additional medical cost. Not good, but not as bad as the other way around. If a person has tumor, but we predict as normal, then it may cause life loss. So in these cases, the two types of errors obviously have different importance or preference. So therefore, if we just want to find a classifier that minimizes this risk, this RH, instead of individual ones, we may result in a type of error that is very large and we cannot afford. So therefore, we need a way to construct a classifier to prioritize the error, the type of error that is more important. And we call this asymmetric error control. So before I jump into our paradigm, I want to make a distinction between a population classification error and an empirical classification error. So as you can see in the definition, here the type 1 error here, R0, it's based on the probability, which is based on the whole population, not just our training data or our test data. So let's use this cartoon as the example. So why is controlling the population error is important? So in this example, if you want to watch the YouTube cartoon, it's actually in this link. And I'm just going to explain it using some images. So in this example, we have the whole population of people plotted here, and the color indicates their health characteristics. So the more reddish means the person is more diseased, and more bluish means the person is more healthy. And the plus and minus sign means the person has disease, a plus, or minus, not a disease. So therefore, we want to draw a threshold on this single feature to decide whether this person has a disease or not. Then the question is, where to set the threshold? If doctors want to control the false negative rate, that is the type of error that the person is diseased but we predict as healthy, under 1%, while minimizing the false positive rate. If this is our objective, then what should be the diagnosis threshold? So here I'm just giving 5 candidate thresholds. So you see, for each threshold, I would call these people as diseased. So as the threshold becomes less and less stringent, more and more stringent, I will call more and more people as diseased. So out of those 5, which one is better, or which one is the optimal? If we can observe the whole population, it's not a difficult problem at all. Maybe a middle school student can do it. You can just do the counting, right? You can just count where is the 1% false negative rate threshold, and that is threshold 4. So we can just come to this calculation. However, in reality, we never get to observe the whole population. Instead, we just observe a random sample from the population. So given this random sample, where to draw the threshold? You may still do the counting and find where the 1% false negative rate is. Just do that counting on the sample. And then you will get threshold 2. However, we know that if we know the population, this threshold would actually correspond to a false negative rate at 7% instead of 1%. So you pick a very bad threshold. And if you repeat this process by observing different samples, we will get a distribution. So sometimes we'll pick those thresholds, sometimes we can pick the optimal one. But there's no guarantee that we will pick threshold 4 or threshold 5, which can guarantee my population false negative rate under 1%. So therefore, for about half of the chances, I will pick a very bad threshold. So this example suggests that we cannot simply just draw a threshold from a sample if we really care about the population type error. Okay, so motivated by this toy example, now let's talk about our formulation. So this is the formulation of the Neyman-Pearson paradigm I'm going to introduce. So the question is that we want to construct a classifier so that its population type of error, which is the more important error we care about, is no more than alpha. So alpha is the threshold you set beforehand, say 5%. And because we said the classifier is trained on a random training data. So that's why we cannot say this R0 H hat, which is a random quantity, because the randomness of H hat to be under alpha for sure. So there must be some violation of this fact. So we just denote this violation by another quantity delta. So we have 2 parameters. One is the type 1 error upper bound, alpha. The other is the violation rate delta. So you can consider violation rate as your tolerance level. So how much tolerance you can afford to have your population type 1 error more than alpha. So with this formulation, then our question is, how do we find this H hat from our training data? Okay, so you may wonder, why is this formulation reasonable? So in practice, if you read about some FDR regulation, you can see that it's better for people to understand probabilities than some random parameter settings. So for example, if I say, okay, in my objective function here, if I modify these 2 weights to be something different from the probabilities of class 0 and class 1, I can also say putting this weight to be large, so I can achieve a small type of error after I optimize the problem. However, it's very hard to say how to understand this weight in a real problem. On the other hand, if I say I want my disease diagnosis to have false negative rate under 1%, this is something everyone can understand. So that's why we think this setting has a lot of real connections and is very well motivated. Okay, so given this formulation, like I said, if we just modify the weights, this is a field called cost-sensitive learning, which has been well studied in the engineering field for years. So people just modify the weights to try to find the classifier. But in health sciences, there's usually no consensus way to assign costs. And sometimes it's not even ethical to say, like, a life is how many times more worthy than something else, right? So we cannot say the cost has a good meaning. And also, if we really care about the population type 1 error, there's no clear way to decide what the cost or weight should be. And the second thing I think a lot of the audience here must be familiar with is the ROC curve. Let's say we can draw an ROC curve and find a threshold over there, right? So if we vary the threshold on our classification method, then we can draw an ROC curve and we can find somewhere here whose threshold satisfies the type 1 error is in this area. But the point I want to make here is that when we plot an ROC curve, we have to use empirical type 1, type 2 errors because there's no way to directly observe the population type 1, type 2 error unless we can observe the whole population, but that is not realistic. So I'm going to show you an example that if you directly use ROC curve and directly target an empirical type 1 error to be alpha, you will not achieve population type 1 error control. So in this simple toy example, we just have two classes, and each class just have one feature and Gaussian distribution. So in this case, we know that our classifier is just a threshold on the feature. So if it's greater than a threshold, we predict class 1. Otherwise, we predict class 0. And based on this toy example, we can have a closed form formula for the type 1 error, population type 1 error, and likewise for the population type 2 error. Okay, so that can help us evaluate the performance. So here we just do training sample, draw a training sample with size 1000 from this distribution. We separately or independently draw a test sample with the same size, and we repeat this whole simulation for 1000 times. So for each time, we can use our training sample to find a lot of candidate thresholds, and then we use our test sample to draw the ROC. So the ROC is based on empirical test type 1 and type 2 errors. So if my target type 1 error is alpha equals 5%, the most reasonable way is to draw a vertical line at 5% and find the corresponding classifier on it or to the left of it. So here is this yellow one, so we get one classifier in our simulation 1. Simulation 2, we get another classifier. Repeat this for 1000 times, we get 1000 classifiers. So if we plot the test empirical type 1 errors of those classifiers, of course, the way we chose them will guarantee they are all below 5%. However, if we evaluate their population type 1 errors using our closed form formula, you see that a large percentage of them are actually above 5%, which means that we cannot use this simple approach to guarantee population type 1 error. So ROC, obviously, if you want to compare two methods, say logistic regression and random forest, say they intersect here, but it's unclear to us where does this intersection correspond in terms of population type 1 error. So in other words, we say that the empirical ROC space provides no direct information on the population type 1 error control. So that motivated us to develop the Neyman-Pearson classification. So just as a contrast, before I talk about how we implement it, so in theory, we talk about oracle classifier. So oracle means that you just do optimization on the population quantity instead of the empirical quantity. So what we call as the classical paradigm is the objective to minimize the risk so as to find the classifier. While under Neyman-Pearson, our goal is to find a classifier with type 1 error under alpha, and then we try to minimize its type 2 error. So it's a constraint optimization problem. And alpha is something you have to define previously because it reflects your attitude towards the type 1 error. This is the ideal situation, the population. And where the name came from, I want to briefly mention the name. So if some of you have taken a mathematical statistics class, you must have heard of this Neyman-Pearson lemma. And this is where the name came from. So Neyman-Pearson lemma, maybe many people will agree that it's one of the two most important results in the foundation of mathematical statistics. So the other one is maybe maximum likelihood estimation. And this one is very important because it told us a way to construct the most powerful test. And the idea is that we can do likelihood ratio test. So it is the theoretical justification or foundation for likelihood ratio test. So basically, it says that if you really want to have a very powerful test, the most powerful test, then your decision should be based on the ratio of your likelihood under the alternative hypothesis over the likelihood under the null hypothesis. So you see that in this lemma, the two persons, Neyman and Pearson, they proved that this test is the most powerful. In other words, it means that it can maximize the power subject to the type 1 error constraint alpha. So then you can see it is exactly our problem under the classification setting, because we also want to achieve this constraint as our type 1 error control. And maximizing the power in the testing setting is equivalent to our minimizing type 2 error in our classification setting. So realizing this connection, then we borrow the name Neyman-Pearson. So because in this tutorial, I want to introduce the practical part. So I skipped all the theoretical part of the Neyman-Pearson paradigm. So we will directly jump into the algorithm. So this umbrella algorithm will work with most currently used machine learning algorithms to achieve the type 1 error control. So what we call these classifiers as scoring type classifiers, or I should say scoring type classification methods. For example, logistic regression. So these methods are the ones that can output some classification scoring function or scores, and then you can apply a threshold to those scores to make a binary decision. So in terms of logistic regression, the scoring function is just the output. We call this, in statistics, we call this regression function, but I know in some few people call this the estimated posterior function. So you can have this estimated after you fit your model to the data. And then in logistic regression, under the classical paradigm, which is this one, the classical paradigm which everybody uses, then we have this threshold by default as 1/2. So in other words, if your predicted probability of y equals 1 is greater than 1/2, then you output label 1. Otherwise, you output label 0. But in our setting, this threshold becomes something we need to estimate. It's no longer by default 1/2. So then we put the classifier in the form as the scoring function greater or equal than some threshold. So our assumption is that for class 1 observations, they will receive a higher scores than class 0 observations. So this is an underlying assumption. So just to summarize, under the classical paradigm, just as in logistic regression, only the scoring function needs to be constructed or estimated. But under our Neyman-Pearson paradigm, both the scoring function and the threshold needs to be estimated. Okay, so again, I repeat this formulation. So our goal is to find a classifier whose type 1 error is largely under alpha with large probability. And if it's greater than alpha, then the probability must be small. And here we set the upper bound to be delta. So we have alpha and delta. And how our algorithm works. So it's based on sample splitting. We will split the training data into two parts. So one part is a mixed sample of classes 0 and 1. And based on this part, we will train an algorithm, say logistic regression, to obtain scoring function. And then we will apply the scoring function to the left out class 0 sample to obtain a set of classification scores. And these scores are all from class 0. So then the next question is, can we find a threshold from this set of classification scores? So this threshold search step is the key step. So our goal is to choose the smallest threshold among these scores so that the violation rate, which is the green part we call the violation rate, is no greater than delta. So this is the criterion for us to find the threshold. And how do we achieve it? Like I said, in a real problem, we can never observe the true or population type 1 error. But interestingly, even though we cannot directly observe the R0, but we can directly control the violation rate. And the technique we use here is order statistics. So we will use the distribution of order statistics to achieve this magic. And just as a side note, for this, because this project lasted 2.5 years, before we realized the magic of order statistics, we used a very brutal force strategy, that is to do bootstrap. So we just use bootstrap to estimate this violation rate and to control it under delta. But then we realized that, interestingly, no matter how we change our input data, the resulting order seems very consistent. So then we realized that there must be some math behind the phenomenon, and then we found that the order statistic technique can help us do it. So this can help us save a lot of computational time because we do not need to do bootstrap, but just some closed form calculation. Okay, so I'll just quickly go through this because this is not my focus. But this is the result we would use. And you can find this result in any graduate level textbook about order statistics. So it's like for any order k, we can have its right tail probability in this form. Okay, and then if we just make an interesting modification to the right-hand side, to the t here, so you can see that by changing t to this quantile, then on the right-hand side, we can get rid of the distribution function. So this is a nice form. And based on this nice result, we obtain the key theoretical result for our algorithm. So I'll just give the technical details, but let's focus on the conclusion. So the conclusion just gives us an upper bound, you see, on the violation rate. So the violation rate only depends on the order, k, and the left out sample size, m, and our alpha. So with those three quantities, we can have an upper bound on the violation rate. And why is this important? This remark is very important because you see, this Vk is this term, okay, the upper bound, so which is this part. Given the upper bound annotation Vk, we can see that if we want to control this under delta, then we can reversely solve the order we want, and that's our k star. So with this k star, it is the threshold that can guarantee the type 1 error control with high probability. Okay? And also, another nice result for this, nice conclusion from this result is that we can solve a sample size problem. So basically, if we want this Vk violation rate less or equal than delta at least held for the largest k, which is m, then we can reversely solve what is the sample size we need to guarantee the control. And it only depends on the violation rate delta and our type 1 error upper bound alpha. So this n is the left out class 0 sample size. That means at least for the left out part, we need to have this sample size. So I think for a lot of people who need to know sample size before they do this, this will be a very useful information. Okay, so I'll just repeat the algorithm to summarize. So basically, we divide our training data into two parts, a mixed part and the leave out class 0 part. Alpha is the type 1 error upper bound. Delta is your tolerance level for the violation rate. And also, to make our algorithms robust, we do multiple random splits. So the algorithm holds for every split, but if you do random split, multiple split, and combine the result will be more robust, just as we expected. So this function is just the theory part. So how do we calculate the order statistics to find the threshold? And with this order, so then what we do is that, like I said, we split the training data into two parts. One part is mixed, one part is just 0, class 0. So for the mixed part, we train the algorithm to obtain a function, a scoring function. By applying the scoring function to the left out class 0, we obtain a set of scores. And among those scores, we sort them, okay? And after sorting them, I just directly apply the order found by my theory, so I can get the threshold. So with the threshold, with the scoring function, I get my classifier. So every split gives me one classifier. And by having multiple splits and by combining the classifiers together, I get an ensemble classifier. So that's the whole story for the algorithm. And now back to the toy example. Let's see how it works. So still, we try to find the threshold, but we no longer use the empirical type 1 error of the ROC to find it. Instead, we use our algorithm. And then you can see that even though for the test empirical type-1 error, we cannot control it perfectly under 5% because this is not our target, right? And we do not care about this. It's still pretty small. But if we move to the population type-1 error, now you can see we have successfully controlled it under alpha 5% with high probability. So only 4.1% of the type-1 error, population type-1 errors are larger than alpha, which is totally different from the previous result. So just following this result, then we said ROC space does not serve the purpose of comparing population type-1 errors. Then should we provide a different or a new graphical tool for evaluating NP classifiers? And we did. So we call this NP-ROC, which is specifically designed to compare our paradigm, classification methods under our paradigm. So I'll just quickly go through this, but in order to plot this, you have to additionally leave out some class 1 sample to plot the NP-ROC. And this makes sense because sometimes we need to pay a price to know how we will do in the future. So if you want to know more information, you have to leave out more data from the training for the evaluation purpose. So how it looks like is that for each classification method, as we vary this type-1 error upper bound, which is the alpha, we can draw a vertical line to represent a lower bound and the upper bound of the type 2 error. And once we connect them, we will get a band. So we call this NP-ROC band, which gives you the uncertainty in the training process. So just as one simple example, if we compare two methods using the NP-ROC band, one is the red band, one is the black band, then we can tell you in which alpha region, which method is doing better. And that's the NP-ROC, a very short introduction. So lastly, so this is our work. Actually, I should change it from ongoing to kind of completed, but it's not published yet, so it's still fair to call it ongoing. So this is another work under the paradigm, which is about feature ranking or feature selection. So our goal is that if we really care about this type 1 error control, for example, in disease diagnosis, then when we try to find important features for the diagnosis, we should respect this control. So which means that we should do this under our paradigm instead of a classical paradigm. So for this purpose, we developed a quantity called Neyman-Pearson criterion, NPC, which is kind of similar in essence to like AIC, BIC, etc. So which you can use to do model selection, to compare models and to decide which one is better for your prediction purpose under the type 1 error control. So I will not talk about this detail, but if you're interested, we have this paper on arXiv. So for this part, I will just quickly summarize. So I introduced the binary classification, and the key question here I want to address is where's the randomness? So I emphasize that the training data is random, and we have to distinguish the empirical type errors from population type errors. And for the Neyman-Pearson classification, I talk about the goal is to control type 1 error with high probability, and we have an umbrella algorithm that works with most machine learning methods to achieve this goal. And NP-ROC is a graphical tool for comparing methods under the Neyman-Pearson paradigm. And also, using the NP-ROC, sometimes if users do not have a clear alpha beforehand, they can use the visualization to choose alpha in a data adaptive way. Okay, and this is our paper, which was published last year in Science Advances. So we chose this multidisciplinary journal because we want to reach broader audience. And also we have an R package for implementation. So since it's released, the package has been downloaded for 10,000 times, so which is quite an achievement for us. So hopefully I think it can be more useful in real practices. And just a quick overview of how the package works. So you can just load it in R, and this is a simple two-dimensional logistic regression example. So if we just run the classic GLM function in R to do logistic regression, this is the type 1 error distribution you get. So mostly around 18%. But if you run our function and choose alpha to be 5%, then you can see that your type 1 error is constrained. So it achieves your purpose. While in the classical way, there's no clear way how to achieve this. So this is just a very simple demo of how the package works in practice. and very simple commands. And so I want to acknowledge my two collaborators, Xin Tong and Yang Feng, who are also faculty of similar stage as I and at other universities, and also my student, Yiling, who is not here, but she works on the last part, the ongoing part about the feature ranking problem, and also the funding agency. So that's the first part of the tutorial. And so for the remaining time, I'll just quickly go over the second part. But I think this part is actually a little bit easier to explain if I skip the technical details. So I call this generalized R-square measure. And generalization means that it generalizes the Pearson R-square to capture not just a single linear relationship. So the goal is to capture a mixture of linear relationships. Okay, so the motivation actually came from gene expression analysis. This was actually for using microarray data. Even at that time, people have observed this pattern. So you see that if we care about pairwise gene relationships, we see that sometimes we should not use just one relationship to describe the whole scatter plot. So here the two colors represent two tissues, root and shoot of this model plant organism. So clearly, the red ones follow one relationship, the blue ones follow another relationship. If we just use, say, Pearson R-square to capture such relationships, we may miss some of them. For example, like this one, we may miss it. So to generalize this question, it's actually related to the what we call Simpson's paradox. So which means that if you look at part of your data versus look at all the data, your conclusion may be totally different. So in this case, if we just compute Pearson correlation using all the data points, we'll get a value close to 0. But if we compute Pearson correlation for the red dots and the blue dots separately, we may get very strong correlation. So this is Simpson paradox. And another related example, or if you do Wikipedia, check Wikipedia of this term, you will see this is a very phenomenal paper in 1975 on science about sex bias in graduate admission from Berkeley. And my PhD advisor was actually the first author of this paper. So what this paper said is that if you look at the graduate admission data on the whole thing, you would think there is some discrimination against women. But if you look at the admission rate department by department, you do not observe this. And the reason for this discrepancy is that a lot of women apply to departments that in general have very low admission rates. So that's why overall you see the admission rate for women is very low, but by department you don't see that. And this is a perfect example of Simpson's paradox. So in this case, it's like if you look at stratified data, you see strong correlation. But if you look at the data as a whole thing, you do not see the strong correlation. Okay, so in the field of capturing the relationship between two one-dimensional variables, there are many, many methods. So I'm just doing a summary here. So I categorize those measures into two types. One I call functional, which means that they aim to capture one-to-one relationships. For example, Pearson correlation is for linear relationship, Spearman rank correlation, Kendall's tau for monotone relationships, and some other newer measures for more general functional relationships. The other big category is that I do not care the shape of the relationship. I just want to capture anything deviated from independence. So anything that means dependence will be captured. So that includes, for example, the famous mutual information, etc. So I want to stand somewhere in the middle between the two types. So we want to move beyond functional relationships because we realize sometimes the relationship may be a mixture of one-to-one relationships. So it's non-functional. However, we do not want to be so general as any dependence. So we still want the relationship to be interpretable. That's the purpose. Okay, so just another summary. So from functional, linear, monotone, general to any dependence, we see the flexibility becomes better and better. However, the interpretability becomes worse and worse. Linear is the most interpretable one. So that's why Pearson correlation is so widely used. Okay, so we are motivated by the fact that a mixture of linear dependencies is widespread, easy to interpret, but we do not have a powerful measure to capture it. So this leaves room for research. So over 40 years, there are in many fields like statistics, economics, social sciences, and machine learning, there are many papers about capturing mixture of linear dependencies. However, they do not provide an association measure. They are either about model parameter estimation or they're about algorithm. So basically, they just want to fit some lines through the data, but they do not provide a scalar measure which you can use to measure the strength of the relationship. So this is our question of interest, how to derive an association measure. So I started the problem by thinking about two cases. The specified case is the simpler one. So just like in my gene expression example, suppose that I know the tissue is a good separator or indicator of the membership of the two lines. Then I'm in the specified situation. So this indicator told me that which data point is in which line. So with this, I'm in the specified scenario. While in the unspecified scenario, I have no knowledge about the indicator variable. So I have to learn totally from this pattern. And this is more challenging. But for my methodology development, I started from the specified scenario because it's easier and it can give me some foundation for the unspecified scenario. So in the specified scenario, the idea is that I started with each line. So for each line, I can have the R-square for that line. But here the indicator can take k possible values, right? So from 1 to k. So therefore, I take an expectation over this indicator z. So that what I basically get is a weighted sum of the R-square of different lines. So I just take a weighted sum of the kth lines R-square. And here I'm in the population situation, which means that I did not talk about sample. I just talk about the joint distribution of my random variable x and y and the indicator z. So this is my first formulation, the specified population generalized R-square. And how do I move from this to the unspecified case? So the idea is that I want to use lines to represent each component or each cluster. You can consider it that way. So therefore, what I do is that for each k value or each component, I define a center. I call a line center. And the line center is defined as what? As the line that has minimized the perpendicular distance from any data point to that line in terms of the expectation. So the idea is that my measure wants to be symmetric between x and y. So in this case, I do not have which one is the response, which one is the explanatory variable. So they are symmetric. So therefore, to measure the distance between a two-dimensional point to a line, the most reasonable one is the perpendicular distance. Right, so then what I do is that I take over the expectation over the joint distribution of x and y, and then I find the line center that minimizes it. Okay, so I'll quickly skip this, but just for your information, in the population sense, the line corresponds to the first principal component of that component. So for every component, I just compute the first PC, and that's the line center. Okay, so on the sample level, so moving from joint distribution to a specific sample from that distribution, I can define my sample generalized R-square, which is just moving from population to sample. Nothing special. So the proportions are the proportion of the kth component in the sample, and this R-square is the sample R-square based on that sample. Okay, so specified case is not difficult. Unspecified case is more difficult. Especially if I really want to have some population quantity so I can do statistical inference. So the population quantity is definitely based on the specified case. So I'm still trying to define k lines. But here the k lines can only rely on the joint distribution of x and y, not z anymore. I do not have the indicator variable. So I define the k line centers, population line centers, by minimizing this quantity. That means for every point, I calculate its perpendicular distance to its closest line center and square this distance. So out of this, for this minimized distance, I calculate expectation. And then I find k line centers that minimize this whole thing. So the idea is that I try to find k lines to best partition my population of X and Y. So that's the intuition behind it. And with this definition, totally in theory, because we are talking about the distribution, not a sample. So this is an explanation that they're different. So for example, if I know Z, you see that my two line centers are these two. But if I don't know Z, based on my definition on this page, the two lines will actually be a little bit closer to each other, because that's my best guess, since I don't know which one is which. So my best guess is to do the partition of into two components, and that's the two lines I got. So just to explain their differences. Okay, and so with these K lines, then I can introduce another variable Z tilde based on just X and Y. So you see that Z tilde will just be depending on X and Y, and it is the indicator of which line that X and Y is closest to. So based on the K lines, I can assign X, Y to one of the K lines. With this Z tilde definition, then I would have my unspecified population generalized R-square. So I still have the K components, but they are not specified by Z because it's not available. It's specified by Z tilde. So following the same formulation, I have my unspecified generalized R-square. And furthermore, for the sample version, to achieve or to find the K lines, I actually derive an algorithm to minimize this objective function. So the key thing is that I changed expectation to this average on the sample level. And this is what I call the K-lines clustering algorithm. So basically, it can cluster my two-dimensional points into K-lines. And the idea is very similar to K-means algorithm. The main difference is that the cluster centers are no longer points, but they are lines. And also the distance metric between a point and its center is the perpendicular distance. So that's the key point. And with this, after I assign my points to lines, I can have sample level surrogate index for each data point, which is which component or which line it belongs to. And then with this, I can have my unspecified sample measure. So I have my unspecified sample generalized R-square defined similar to my specified case, but the indicators are from the K-lines algorithm instead of observed. So to summarize, I have four measures: the specified population sample measure and the unspecified population sample measure. So for the theory part, the most challenge or the most efforts were spent to derive the asymptotic distribution. So I just show one result. This result suggests what? So for the sample level unspecified measure, it follows asymptotically normal distribution, and the center is the population version. So with this, why is it important? With this, basically, we can use our sample measure to do statistical testing, and we can use it to construct confidence intervals for the population measure. So everything can follow. So let me just quickly move from here. This is a simpler version if we assume some Gaussian distribution, but without Gaussian assumption, the general result still holds. Okay, so this is just some simulation to show to you. Here, the dotted line shows the actual distribution of my sample measure under each setting and under each sample size, and the solid line is the solid line is the simulated distribution, and the dotted line is my theoretical calculation. So you can see that they actually agree pretty well in most cases, which means that asymptotic distributions are working well. And this is from a normal simulation, and from a t-distribution simulation, I obtained similar results. So this is just the confidence interval construction. So to summarize, what I've compared here is that using my theoretical calculation based on the asymptotic distribution versus bootstrap. Because bootstrap is sometimes something people use a lot in practice to get confidence interval. But I want to show that using the theoretical results, we can save a lot of time from computation. We can just use the closed form formula to do the confidence interval construction instead of doing bootstrap. Okay, and another critical question is, how do I choose K in the unspecified case? Because K is not known beforehand. So just as in the clustering problem, we propose two solutions. The first solution is to look for the elbow points in the within cluster variance. And the second solution is that we develop AIC quantity based on some distribution assumptions, because it's a likelihood-based measure. And AIC want to minimize it, so we can find that the minimum AIC corresponds to the true K in my simulation and also in this simulation. So we propose 2 strategies for choosing K in real practice. And furthermore, this is a simulation result for power analysis because this is something we really care, right? So given what we want to discover, is the measure powerful? So in this pattern and this pattern, so you see both are the cases where they have more than one relationship. So clearly we see that using our measure for 3 different sample sizes, the blue curve is the power of our measure. It clearly is the best and it's better than existing measures, including Pearson R-square, which is pretty bad here, and also maximal correlation, distance correlation, and another method called MIC, which was published in Science in 2011. So just quick power analysis shows that our measure is powerful for capturing such patterns. And lastly, so for real data application, I think this is an interesting example. So we look at that Arabidopsis RNA-seq data, and we look at gene pairs in the pathway called GSL. So genes in the pathway are supposed to be more functionally related than some random gene pairs. So therefore, if a measure is meaningful, then the measure should have a distribution that towards more higher values for the GSL pairs than random pairs. However, if we compare R-square, maximal correlation, distance correlation, and MIC, we see that they all have more higher values for random pairs than the GSL pairs. However, if we use our specified GR2 using tissue as the indicator, because based on our previous observation, tissue is supposed to be a good indicator, then we see, yes, GSL genes have higher correlations or have higher measures than random genes. But if we use other indicators which we know wouldn't work, like condition, treatment, replicate, these are also variables in the data set, but they are not meaningful, then we see using our generalized R-square measure, we also have patterns similar to just Pearson R-square, which is expected. But using our unspecified version, which means that we do not know which is the indicator, but we just specify K equals 2, then yes, we see that we can effectively show that GSL genes have higher measures than the random gene pairs, which again demonstrate that we can use the measure to screen for interesting gene pairs. Okay, so I'll skip this application and summarize. So for this measure, we propose something as a generalization of R-square to capture a mixture of linear dependencies. And we have 2 scenarios, specified scenario with indicators and non-specified scenario without indicators. And we provide statistical inference for the measure and also a K-lines algorithm. So there's some future research directions. The most important one is that we can extend this to rank-based so that the measure can work with monotone transform data. So finally, acknowledgement, a paper, and still on arXiv, and also the R package, and acknowledgement from my collaborator and my PhD advisor, because this project has lasted for multiple years. So thank you very much.